Thank you very much for the introduction. As Hannah just outlined the program of quality assurance guidelines, she already mentioned briefly some of the guidelines for interstitial hypothermia. Just as a short reminder for those who are not familiar, interstitial hypothermia utilizes an implant of applicators into the tumor. And for that purpose, a number of techniques have been developed, including mostly electromagnetic methods, but also ultrasound has been used for this purpose. And as also outlined, the previous guidelines in this field are actually quite old. So that was the reason for us to come with updated guidelines for this specific topic. And these are the recently published guidelines. As you can see, quite fresh. And these were actually composed by members of the technical committee of the ESHO, including also senior members from the American or the North American Society of Thermal Medicine. And we did this under the guidance of the Atzelsberg Circle, which is regularly coming together in Erlangen. So, first of all, what were the topics touched upon in these guidelines? Well, requirement on the heating devices, but also how to characterize the heating properties, and preferably so in a fairly straightforward and simple and fast manner. How to conduct your thermometry, items on the workflow for interstitial hypothermia, and also the staff requirements, as also mentioned. So the requirements on the heating devices. First of all, important requirement is that there should be sufficient power available to achieve 44 degrees centigrade in the target region. And in general, that means also including the local perfusion. So that means that you should have about 500 watt per kilogram locally. That sounds like a lot, but actually this is in a very small subvolume. It also means that if you're using catheters to insert your applicators into, that these should be composed of a lossless material or a low loss material. The heating properties. Well, first of all, we outlined what sort of properties are required for the single applicator. And we decided that in view of the very localized heating pattern, that we used a calorimetric method to characterize the applicators. So that means you insert the applicator in a cylindrical tube which contains a saline, and you heat for a specific time period, and after the time period you should have sufficient temperature elevation. And that means you're independent of the specific SAR pattern of that single applicator. You also look at the SAR pattern itself, and this is shown in the central panel. And by doing so, you also characterize the effective heating length of your applicator, so that you are aware what is the size, the maximum size of your tumor lesion which you can heat with that applicator. Next, a very important issue, we're rarely using a single applicator, always an array of applicators. So what we require is that all these applicators can be steered independently. And as already shown in the previous presentation, that means that we compare the SAR patterns with single applicators switched on and off. And if that does not impact the SAR pattern of the neighboring applicators, then we think that the system is working properly. Thermometry, also quite important. As also already mentioned, we get this sort of temperature patterns within an interstitial implant, with very high temperatures very close to the applicator and the minimum temperatures in between. And this is just a theoretical sketch, but you can appreciate that it's very important to know where am I measuring the temperature. So you could have thermometry integrated with the applicators, and that would mean that you measure at that location the maximum temperatures, but you could also measure in dedicated thermometry catheters in between your antennas. And that means you measure at that location the minimum temperature, as shown here. So it really depends on the technique used, whether it's possible to combine thermometry with your applicator. In most cases, you will have to insert additional catheters for your thermometry. And in that case, you get the minimum temperature, which is also quite relevant parameter and possibly more important than the maximum temperature. I will return to that. So, workflow. The process of workflow for interstitial hypothermia does involve, first of all, a pre-planning of your implant, which is quite important, because this is the moment where you really determine your heating capability within that implant. Then you implant the catheters according to that plan. Then the next step in the third image is that you verify whether your applicators, your catheters are at the designated location, and then you do the real treatment planning. You perform treatment, then, and at the end you make certain that you document all the relevant parameters. So the pre-planning is shown here. Typically the spacing will be identical to that in a brachytherapy implant, so let's say typically 10-15 millimeters in between the probes. Then the planning will need to look at the target region and also at the organs at risk. So imagine you're heating a prostate, you probably want to spare the urethra, and then you determine the number, location of the applicators, as well as the location of your thermometry. You implant according to that plan, and this is again, what sort of spacing do you need? Usually with a very high perfused region, which most of our locations are, the implant spacing needs to be something in the region of 10 millimeters in between. Otherwise you get cool spots between your applicators. And you need to assure that you have parallel implant and alignment, because otherwise you might have a risk of cool spots and also hot spots. Then you reconstruct using, for instance, CT, possibly MRI or ultrasound, and you determine the GTV and the target volume. Treatment planning. You have to determine insertion length and position of each catheter, and the location of the applicators and the thermometry probes. Steering parameters, and then you start your treatment. And as said before, the treatment should have a duration of 60 minutes, preferably. Then the delivery. During the treatment delivery, the staff needs to have an image of the power and temperature, and you should very gradually increase power during the first 10 minutes. And you make certain that you document properly all the temperature parameters, and mainly the T50 and the T90, and we want the temperature to exceed at least 40 degrees centigrade. And after the end of treatment, you should still measure the temperature for some time in order to see what the temperature fall off is within that period. So that's the documentation, and the data to be recorded are power, temperature, and it's very important also to look at the cumulative dose. If possible, also including the cooling of the medium, if that's applicable, and commands made during treatment why you decide to do certain changes. So staff requirements, these are the people involved, and we also require that, that the staff has a minimum training of 25. So this is the publication. Are there any questions?
Thank you very much for the talk. Yeah.
Sorry, one question that you told we need about 500 watts per kilogram. With what effective ratio? So what is the effectivity of the output power which is going into the tumor or into the target area?
That is dependent on the size of the tumor target area. So
the effectivity is not depending on tumor size. So
no,
how many percent of the power is going into the target?
This is really the power you get from, let's say, this is the power density you require. So it depends on the size of your region and the number of applicators you use, how much power in total you're using.
So the 500 watt power is the output power or the power which is going into the tumor?
The 500 watts was per kilogram.
Yes, I understand.
Yeah,
yeah. But 500 watt per kilogram is the output power of the...
It should go into the tumor. It's not the nominal power.
But 500, so if you put 500 watt in 1 kilogram, you can burn it in 5 minutes, the whole
yeah, but
tumor.
This is extremely locally. So you get very high temperatures close to your applicators, which you usually do not measure. But as you normally combine with brachytherapy, you already accept that there's a very high, that you ablate very close to your, yeah.
It's ablation in the vicinity of the catheter.
So that's very, yeah, and that's in a macroscopic tumor, so that's acceptable.
Okay, then I would like to